Hello everyone, my name is Raphaël Razafindralambo and I'm a Ph.D. student from Enria Centre Université Côte d'Azur, and I'm glad to present you our work on Ensemble of Diffusion Models when are two scores better than one. We gratefully acknowledge the 3IA Côte d'Azur for supporting our work and for hosting this video on their YouTube channel. So in this paper, we study ensembles of diffusion models, an approach that has received little prior investigation. And what we reveal is surprising findings. The impact of ensembling on image quality is more subtle than expected. So now let us start with a quick introduction on the topic. So what are diffusion models? Diffusion models constitute a popular class of generative models that leverage stochastic processes to typically produce highly realistic human faces, as you can see in these examples on the left. And so to achieve such level of relevance and details, diffusion models can rely on many strategies, such as using big neural network architectures, long training time, or efficient training and sampling processes. Now, there exists a class of methods in machine learning widely used in supervised settings to improve performance by aggregating the outputs of a set of predictors, but largely overlooked in diffusion models, and this is the class of ensemble methods. Actually, they were popularized in deep learning in the name of deep ensembles, notably for uncertainty quantification. And so it consists in training k neural network in parallel with same architecture on the same dataset, but with different seeds for the initial weights. And one reason ensembles are so popular now is that they have repeatedly been shown to improve performance empirically, with theoretical results further supporting these observations. And so the goal of this paper is to investigate ensembles in the context of diffusion models, and what we show is that the problem is surprisingly challenging. Now let us do a quick introduction on diffusion models. So what is the big principle? Diffusion models learn to reverse a process of adding noise to data. So we consider two diffusion processes, each written as a stochastic differential equation. So the first process, which is above, is called the forward process. So this one describes the transformation from data to noise, and this process is fully known, with all coefficients known. So this process is different from the second one, which is called the backward process and which is written below. So this one describes the transformation, the reverse transformation, namely the transformation from noise to data, and is unknown as it relates to an unknown time-dependent gradient field, which is a Stein score in the blue box. And so, as you could guess, the goal of diffusion models will be to learn to approximate this vector, typically with a neural network, so that given f and g given from the forward process, we can start from noise and solve the backward process to recover the good data. So now let us ask two questions that will be essential if we want to build an ensemble of diffusion models. So the first one is, how do we learn this time-dependent score? So the way we do it is very simple and is regression. So now let S theta be a unit with two entries, so for which the weights are shared across time steps. And so we optimize this single model on an MAC loss, taking an expectation over time steps. And more precisely, we minimize an error against a tractable conditional score, given the clean data from training set x0 and the non-forward process. But now, the second question, what about sampling? So we want to solve the backward SD, right? And so to achieve this, we rely on a discretization scheme, such as Euler-Mariama steps. And so what we do is that we start from noise, and then iteratively, we follow this rule from last step to step 0, using the trained neural network at each step, as you can see here. And at the end, we expect the data to follow the training distribution, or to be a good approximation. Based on these principles, we can now design a straightforward strategy to ensemble diffusion models. So what do? We train k models in parallel using the type ensemble method on the objective we just defined previously. And then at inference, while at each step we would normally forward pass one instance of neural network. Instead, we leverage all the models we trained earlier. And then, so at each step, we combine their outputs through an aggregation function denoted like here. And typically, it could be the arithmetic mean as it is traditionally done in regression. But before going to practice, let us motivate ensembling through an interesting result. Consider this aggregation rule, the arithmetic mean, and so we show in proposition 4.1 a monotonicity result on averaging. And what we show is that in expectation, K plus 1 models is better than K models for the denoising score matching objective. So it is a pretty interesting result. So this one is classical for regression, but here we extended it to the diffusion models framework. And the proof is in appendix C.1 and it's straightforward by using Jensen's inequality and exchangeability of models. So based on these results, we tried a simple application of the deep ensemble and arithmetic mean on a human face dataset named FFHQ. And what we figured out is that it is not that simple. So here we measure image quality using the perceptual and feature-based metric FID. So what do we see? In the first line, we display samples from the strongest model within the ensemble. In the second line, it is the weakest one. And the last line, it's the ensemble. So on the right, we report the FID, and the lower is better. And as you can see, while ensemble managed to beat the average FID, equal to 24.2, it does not beat the best model with 21.7 of FID. So it is a surprising result given that in supervised setting, ensemble generally beats the best model as soon as the ensemble size is 2. And here we have 4. And the problem is that given the cost of ensembling, we would expect ensemble gain to be better than marginal. So that's why, based on these results, we investigated various aggregation schemes, datasets, and metrics to identify factors that could solve or at least explain the lack of improvement we just witnessed. So here you can see the table 1 from the paper, which can be found on section 5. And so what it basically says is that for image quality measured by FID and KID, the gain is at best marginal, in the sense that we do generally not beat the best model. However, if we ignore image quality or FID, which I agree is a metric of interest, we can see that ensemble seems to work in some extent. Indeed, just take a look at the left plot. So it is an empirical illustration of proposition 4.1, as it shows that when ensemble size grows, the score loss decreases. In other words, it shows that ensembling does diminishes the objective which each model of the ensemble is trained to minimize. So it is very interesting, and we observe the same kind of results on the right for the negative log likelihood, which is linked to the denoising score matching loss up to some order of derivative. And the problem is that both metrics do not directly connect with perceptual quality, which can explain the discrepancy. So we let the viewer see the last part of section 5 for a more detailed analysis of the gap between score matching and image quality. Now we briefly present additional results, and we refer the viewer to the paper for full details. So on tabular data, we ensemble decision trees and show that a specific aggregation alleviates a prediction bias. We also derive a key theoretical result on the geometric mean of models, corresponding to the arithmetic mean of scores. And what we prove is that, so we prove in the paper, with a Gaussian counterexample and straightforward arguments, that product and diffusion do not commute. which implies that ensembling is, with arithmetic mean is in fact not equivalent to a product of experts, which has broader consequences, including for guidance. So what is the take-home message? So we tried to combine diffusion models and deep ensemble, and what we saw is that while it improved the training objective, it fails to enhance image quality. So what it shows is a misalignment between score matching and perceptual fidelity. And so what this conclusion raises is the question of the cost-benefit trade-off of ensembling. Because what we observe is that the gain is marginal, but the cost of ensembling is very high. So thank you for listening. I appreciate your attention. So please feel free to watch the code on this QR code, as well as the review on this on the QR code associated to open a review. And we thank the reviewers for the constructive feedbacks.